minimize the f. And we have x. X is our variable. And then now I'm going to talk about the general form. So f, well, we previously talked about f as what? Ax minus b, 2 norm squared, something like that, right? But now I'm going to go through it in a general sense. F is a function of a variable x. X is a vector of n dimension, so it's a vector. And f is a function, it maps a vector to a number. Okay, so something like this. And then we are showing this is convex. So again, convex. What does convex mean? Convex means it can be described by something below it. So if a f looks like this, okay, this is a convex f. Why? Because for any point on this function, you can always find a support. What does it mean, support? A line below it. So for example, I'm at this point, I have a line here. This line, you imagine a line here, is globally under this f. So what is a convex function? A convex function is at every point on the graph, this is called a graph of the function. You plot the graph of the function, okay? At every point on the graph, you always find a global support. That means everywhere in the function, you have a line below it for a whole function. So at this point, I can have a line like this. Okay, at this point, I can have a line like this. So what is not a convex function? So for example, if my function looks like this is not a convex function. Why? Because at this point, I do not have a line below it. Here's the thing. You may say, oh, what about this line? This line is below this function. No, I'm saying the line that have to touch the point. So if I have to touch this point at this function, then that means the line something looks like this, right? But this line is not globally under this function because at this point, it crosses over. So therefore, this function is not convex. Another way to see a function is convex or not is, so how do I see this function is convex? Is you pour water, and then you fill in the whole shape by water, and you get a shape, right? A function is convex if this shape is convex. The technical term of this is called epigraph, but I'm not going to go through detail about this thing. Basically, it's just epi means on top. Everything above the thing, above the f, things above the f. So this is epi, okay? This shape is a convex shape, okay? So this is the idea. And then, because of this, we can have what? A function that is below this function, okay? Another function. So now I'm calling a function a straight line. So f is always what? Larger than an L. L is a function, or maybe I call it a line, okay? Line x. Okay, I call it line x. So what is it? So suppose I have a point here. Then this is my f, right? This is my f. Okay, this is my f. What's my line? So in this case, I'm drawing the dotted line. So this is my line, okay? I have an L. That L is always larger than L. How do we write it explicitly? For a particular x bar, so suppose this point is my x bar, okay? Then I have the following. F at any x larger than f of x bar plus greater than of f at x bar, x minus x bar. So what does it mean? This whole thing is my line x, which is, okay, so something like this. So what the heck is it? This fx is for all x. That means what? I have this function f at any x. So suppose my x is here. This value, I mean on the y-axis, on the height, is taller than this particular value. So that means what? This dotted line is my line x, right? If this is true for all x, then this is convex. And this thing, let me recap, is called gradient. But here, I didn't say f is differentiable. So this thing is also the subgradient, okay? Subgradient is denoted like this. So let me recap. What I'm saying here is that I want to minimize the function f. The function f has the following condition. It's an Rn to R. That means input is a vector, output is a number. Convex. What does convex mean? This. What does it mean? Any point in the function, I can find a point. Then at that point, I can draw a line. And this line has a special property. It has to be below this line, below the original function at any x. So at this point, you can think of this as an anchor point or a reference point. At this particular reference point, I draw a line. This line is below the whole f for any x. Then if this is true for any x bar, that means any anchor point and any x, then this function is convex. So this is the math definition. And why I talk about this math definition? Because this thing here, this inner product, this is f at the particular point, this is a constant number. So this is a constant, this is a number. This is a changing thing because there's x. The only thing that's changing here is this term. What is this? This is inner product. Okay, maybe you forgot. I always write this as my inner product. I don't write A transpose B because confusing. Then this is a changing point. This is a constant. So this is basically the distance between x and my anchor point. This is the gradient at the anchor point. But in case my function is not differentiable, then this becomes the sub-differentials. For example, here, I can have this line, I can also have this line, I have a bunch of lines. So all this line is the support at this line. So let me draw it here. So at this point, I can have a support like this, I can also have a support like this, I can also have a support like this. And for a line, how do you define a line? You define a line by the angle. So this angle here, and this angle here, all these angles are exactly the direction of the line or the plane. Because how do you define a line? You define a line by the angle. So that is the normal to this line or plane. So all this angle here has a meaning of the gradient or the slope. If you think about it, it's a one-dimensional thing. So this is a gradient. And for this particular point, if I have many underline, any support means under it, okay? Then I have many slope. And this is the generalization of a gradient. If I am at a point, let's say this point, I only have one line. So the slope is unique. I only have one gradient. That's why we have this. But this generalizes to anything that is not differentiable. And then you have what? A gradient. And once you have the gradient, you can do what? Gradient method. So you have a new point. This is your new point. Equal to your current point. What? You have a step size, alpha, and then what? You move along the negative direction of the gradient at your current point. This means what? If your function is differentiable, this reduces to this symbol. But if this is not differentiable, then you just compute the sub-differential, which is this, okay? And you keep doing this many times, it will converge. What? It will converge with some number like this, okay? That is saying that the function value towards your best value or best achievable value decrease in this order. Or if I write it explicitly, at iteration k, function value at iteration k minus the optimal value, that means the lowest one, bounded by a bunch of constants, I don't care, divided by k. So if you run k 10 times, it means what? It means your function value at step 10 to the optimal value is dropped by a bunch of numbers which is constant divided by 10. And if you run 1000 iterations, then this becomes 100 times smaller. That means the more k you run, the smaller the error or the closer to the value. And why this is important? Because this is always larger than 0. Why? Because this is smallest value. Smallest value, this subtract is always larger than 0. So you have this. And if these two guys are 0, then this guy has to be 0. So that's the idea. So this is like the overall revision. And this is for the case that this is no constraint. But what if there is a constraint? If we have a constraint, then here we need to do a projection onto this set C. What does it mean? It means, for example, I want to minimize a function like this. This is one dimension. But I restrict my x need to be smaller than 3. Okay, let's say my x cannot be larger than 3. So this is 0, this is 3. Okay, that means what? This part is all the feasible region on x. I cannot have an x here. That means anything beyond this line is I can do it. So how do I do it? Let's say I do some gradient descent. Suppose my point now is at here. This is outside this feasible set C. Because my feasible set is any number smaller than 3. Now I'm here, outside the region. So what I do? I project to the closest point in the feasible set. So that means what? What's the closest point of this guy to the feasible set? Well, which is this point, right? Because, yeah, or in the x-axis, what's the closest point to this region? This point closest to this region by this point. So in this case, I will just project it. Project it basically means you replace this value by the closest point in this set to your input point. So this is called P. And it only modifies the gradient method by you add a projection, okay? And projection, in general, is not easy to compute because some problem, the C is very complicated, then you don't know how to do it. But this will be, we'll talk about it later. So this is like the general idea. And then what's next? You can also do acceleration by what? Instead of X sequence, so you now have two sequences. You have Y and you have X. And you assign your Y as X in the very beginning, and then you do for loop. Okay, what you do? Every time when you update, first you use the Y to update the X. Okay, use the Y to update the X. So I now just write up in this. And then what? Then you use the X to update the Y. So Y will be updated by your new X plus a number, which is called extrapolation parameter of weight. How do we know this number? It will be later. This is some detail. And what we do? We use the current X minus the previous X. Okay, so what does it mean? It means I use my Y, get a new X. Before I get this new X, I have my previous X. I call it X negative. Okay, then this is like new X subtract old X. If you give me a direction, I add this on top of my new X. It's like pushing it away. Okay, then I define this as my Y, and you repeat this this will improve the conversion from here, from 1 over k to 1 over k squared. Yeah, it's a magic, okay? So this is acceleration. So let me recap. We want to solve this. The only condition is this is convex. That's it. We don't assume this is differentiable. If this is differentiable, good. If it's not differentiable, we use the differential. And then just do gradient descent. This is step size. I didn't talk about how to tune step size, but later, okay? If we have constraint, same scheme, just put a projection P here. Projection basically the meaning is you find the closest point in the C that is closer to your point. Okay? And this is like handling constraint. Lastly, what about speed? We can speed it up by doing something like this. So these are all the super condensed revision